From Terracon, we have a whole bunch of offices across the country, but I'm not here to sell you anything, and I'm not a producer or advocating for any of this. Like my companion over there said earlier, I'm not a chemist, I'm not an engineer, just somebody who's actually worked with concrete for an awfully long time. I've been doing mixed design work for probably 32 of the last 36 years I've been in the industry. So welcome, and thanks for sticking around for this tonight. So this is my presentation here is really just to share some of my experiences from using the Type 1L in mass concrete settings. I get a lot of weird calls throughout the year. Somebody will say, hey, we've got mass concrete on a project. I heard you're the guy in the company who knows what to do with this stuff, so I get these calls all the time. And so most of the time I'm spending developing quality systems. All that title stuff up there just really means I do a lot of training and kind of go out and help where I'm needed. So that's kind of what that's all about. So to talk about mass concrete, it's a very different application than the precast industry. Obviously, we're in a completely different scenario than they are. And so it works like this. I'll be sitting at my desk minding my own business, working on some quality manual, making some revisions, doing corrective action responses, and I'll get a call that starts out with, hey, we've got this project. It's got mass concrete on the project. And at that point, it's really not that big of a deal. It's a bunch of data gathering. I get involved. I kind of find out what they know, what they don't know. I ask a lot of questions. I start getting emails. I start getting invited to pre-construction calls. I'll get engineers to send me things. The producers will start sending me mixed design information, and I look at it. But that whole thing actually works normally pretty well until some of the little caveats come in. And so like this first one here, there's a couple of different examples I have here. This first one here was easy enough, except that nobody noticed that it was 5 feet thick, even though it's right there. That was not called out on that project. Nobody said, oh, by the way, we have mass concrete. So that's always an interesting start. So, you know, these images that I have on the screen and the one I showed before, you know, those are from actual projects we've done over the last year, worked on in 2023, and they all involved Type 1L cement in some manner of speaking. So, you know, again, my experience in the past had been from using Type 1-2 cements, some other, you know, supplemental cementitious materials, but not 1L. I'm from the Northeast. I live up in Connecticut, and they are probably the last bastion of waiting for 1L to actually come around to get used a lot. And it's not used. So what do I know about 1L cement? All the gossip, all the rumors, all the horror stories, all the negative things, because that always travels faster than anything positive. So I got all that information. So when it first hit, I'm like, I don't know anything about this. And so it was kind of strange to get involved in this whole arena, using this without having much input. Again, a lot of mass concrete experience using the other things, lots of different projects, some really interesting ones too, but not using 1L. So on this particular project right here, and by the way, I whitewashed this to protect the innocent and the guilty, so I'm not mentioning any names or companies or anything like that in the rest of this. But this particular one here started, and they planned on doing all this project with with a 1S38 blended cement. Again, wasn't an issue. That's what they planned on doing. Granted, they didn't see the 5-foot depth there, but that was what the intention was. And so all of the data, all the preparatory data had been done using that. All the thermal evaluations, all the mix, all the shrinkage, all the testing, all the theoretical data, everything had been done planning on using 1S38 cement. Until they got that phone call that says, yeah, we can't get that. We're going to make a switch, and we're going to switch to this 1L mix. And it's fine. It compares just as well to everything else, so we don't need to do any additional testing. Who agrees with that? You know? Drew did a pretty good job of showing you why that wouldn't make so much sense. So, again, until the ready mix company let them know that that was going to be the thing, and it was a supply issue, and they were just making a switch, you know, and I had to let them know that, by the way, if you're going to do it, we have a whole bunch of extra work we have to do. And so, as you might imagine, others on the call had different perspectives, and all the anecdotal information started to fly about water demand and all these other things. And, you know, it's going to use more water, and the strength is going to suffer, and it's going to retain more heat because it's finer. And some of that is true. Obviously, Drew wasn't lying about anything. He said he was spot on. But again, having that anecdotal information and having our experience, or my experience from the Northeast, and trying to use it somewhere else in the country wasn't lining up. So you guys are familiar with this. This is from ASTM C150, and Drew covered this really well. You know, at that point, you've got a chemistry on your mill certificates. It shows all this information, all the components that Drew talked about, and it's up to the 5%. What I want to talk about, though, is that it's already there in most cases. You're already using 5% in most cases. You're just not paying attention to it. So in a lot of cases when you make that switch, it's really only a 5 or 10% increase from what, sorry about that, only a 5% increase from what you already were used to. So it's not the end of the world, but the mill certificates, depending on what software you're using, if you have homegrown software or using something like Concrete Works software, that's all dependent on the chemicals. You go to use something like Concrete Works and plug this in, and you're going to be lost, because I know I was. So you go through that, and all of a sudden the mill certs don't look the same at all. So here's C150 talking about all the different parts and pieces that go into the requirements, and here's C595. All right. So all of a sudden, you've got some overlap, loss on ignition and equivalent alkali content and all that kind of stuff. But the rest of it, it's very, very different. So because it's a blended cement and all that other stuff, you're looking at the differences here between how the chemistry behaves in the mix, and that has a big deal there. So I'll get back to the story of the project that had that substitution in a minute, but I've got 3 case studies, kind of, they're short, but I have 3 case studies that I want to share with you and tell you how these things went. So, by the way, this is just this is what a mill test report would look like for a typical 1-2 cement. And you can see the blend that he was talking about over there, being at 402. And here it is for the other type, the 1L. So look at the difference right there between the chemistry data that you have on one side on the left versus what you now get with the 1L. Again, it's totally compliant with ASTM C595. That's not the issue. It's that if you've got software or you don't have experience dealing with those changes in the mix, where do you draw the rest of that data from? And so it's quite a lesson to learn there. So project number 1 here is a state bridge construction project in I'll just say the central United States. And this was a whole bunch of bridges that were going to be worked on across the span of about a year. So this is a cut sheet. This is an actual cut sheet right there from this project. And it was going to be several bridges throughout the construction season. And you'll see some typical language related to maximum core temperatures, capped at 160 degrees, max differentials at 35 degrees. It's fairly standard for mass concrete specs. The only real curveball was that they wanted some thermal profiling throughout an entire year. And obviously the seasons change and the weather changes and all that other stuff. So they wanted to have something that they could use throughout the entire year. And again, this is coming from limited information. So the mix that was used, shown above, is typical pier footing. It's got fairly straightforward, except that the environmental conditions across the U.S. have changed. The central U.S. this year was a lot hotter at certain times. It was colder at different times. And so you can't just use historical modeling and assume that everything's going to be the same as it always was. And so they wanted this plan that would fit all their needs. Of course, that's every consultant's dream. Sure, what's the budget? I'll just go forever and keep writing things. It came to a bunch of common sense approaches. But in the back of my head, again, all I had was anecdotal history. I didn't know, is this really going to behave the same way that I know the 1-2 will behave? I just had what I've been hearing from people. So, you know, again, Ready Mix Producer did a great job. They did all kinds of stuff. They did, hey, here's a nice, beautiful aggregate blend. I've got all the intermix in there. We're closing the gaps. We're keeping the paste nice and tight around the aggregate. They had done some maturity testing. Everything looks like it's going to be fine. And so all this stuff is within the limits in the initial calibration curve and everything else. And all this time, I kept hearing that 1L is going to have a higher water demand. It's faster on the startup, a 1-2 cement. So we don't know how it's going to be in production. And again, when I'm saying it's faster on the startup, I'm thinking 7-day strengths, not Drew's 10 and 12-hour strengths. Never considered that for a second. I'm saying faster on start because you're getting really good 7-day strengths. He didn't care about that. Obviously, I do. So after a bunch of lab testing and data modeling, we produced a table of expected maximum temperatures and temperature differentials based on the expected ambient conditions. And, of course, that didn't play very well. So the only good thing was because I had bracketed it all out with temperature ranges throughout a year, they basically went by, hey, what's the predicted temperature range for when we're pouring, forgetting what I had plugged in the months, because Mother Nature threw us a curveball. But the bracketing helped make that make sense. So this is some actual test data here. You can see the actual dates of placement, the time of placement, the concrete temperatures, the ambient temperatures, and what we actually got. So the predicted temperatures and the differentials that were predicted compared to the actuals. Anybody notice anything there? This is just a small sample, obviously, from this one project. So obviously I threw a range of dates in here, and on this particular project I have over 100 sets of cylinders cast throughout an entire year from all these different bridges that were done, so I've got a wide range. But, you know, I picked the colder ones on purpose here, so we've got, you know, from October till February of this year. And we're still doing it now. These projects are ongoing. We're still collecting data. But the weather was the biggest challenge. But on the one that really caught my attention was on February. And so when you have a pattern of behavior where things start to work out in your favor, you get a little cocky sometimes. So on the February one, they kind of pushed their luck a little bit, hitting really close to their limits on their differential temperature, mostly because they pulled things a little earlier and didn't leave the blankets on like they're supposed to. But anyways, one of the biggest challenges we have is that rational thinking in mass concrete changes. And it doesn't change so much because it's a 1L, it just changes that if you have a hot mix, the outside's going to cool faster because the ambient temperatures at this time of year is colder. So you actually have to keep the outside much, much warmer. Otherwise, it's going to cool faster and you're going to have a great differential. Now, I haven't ever seen a case where somebody put on like an electric blanket or heating tubes or something like that or glycol around the thing and it warmed up the center. It's not a person, it's concrete. But the concrete core temperature stays hotter longer because it's finer and denser and the outside does like to cool faster. So it's more than they think it is. They think, oh, I've got blankets on, it's going to be great. And it is initially. But you actually have to increase the heat as it goes. Otherwise, if your outside temperature is dropping like a rock, your differential is going to be out of whack. So that was one of the things that we had to really talk about with the contractor. It had more to do with the curing environment than it had to do with anything else on these projects. And they've placed over 100 sets of cylinders so far. I think we're sampling at like 1 per 150 cubic yards placed. So I've got a good amount of data to support these things. The lesson learned for this particular example is that because of what it was, because we were talking at the state level, because we're talking to people who aren't so time sensitive, they want it done right, they're not sitting there with deadlines, they don't have performance guidance and all that stuff. Communicating early and often throughout the process was really the biggest win for this thing. Going with the data, using data-driven decisions from the modeling we did in the laboratory to the actual mixing and then the testing, that was a whole lot better than just listening to the anecdotal information. And then educating your client, again, that with mass concrete, even though they have done mass concrete before, again, you fall into habits of, oh, it worked last time, so I'll do the same thing this time. Best practices are best practices, and then learn from the data that you've used. So that's number one. The second one comes along, and this one was constructed in June of last year. And if you look at the foundation plan, it looks like it's pretty simple rectangular footing. Has no real complexity. For the most part, that's pretty good. There's just one really interesting characteristic. And here's part of the specs, and that's an actual cut from this spec, and I blocked names out on purpose, but here's an actual cut from the spec. And as you can see, mass concrete's never called out at all. There's no mention of mass concrete in this foundation. So they did, and again, it could be sneaky. I guess you could be a lawyer and look at it and go, well, wait a minute, they did mention ACI 301 and 347, and those are mentioned, mass concrete's mentioned in there, so by association it's in there, but it's not called out and it's not very clear. And so, but there's really no spec for that thing. So of course we pumped the brakes and said, hey, wait a minute, you've got mass concrete. And they said, well, what do you mean? And I said, well, this is what I mean. That's what you have right there. How could you not call that out? I mean, it's not like it's a new topic. Fortunately, the contractor sent the plans and specs so that I could see this well in advance. And one of our project managers called me. I got one of those phone calls. Hey, I got this project, and I think this is mass concrete. Could you take a look? Oh yeah, you've got mass concrete. So we were able to stop and pump the brakes on that thing and get everybody doing it. The good thing is they had already planned on using 1L cement. So although they never planned on having mass concrete, at least they planned on 1L cement and had some data to back that up. So as you might imagine, there's several teams meetings and phone calls and everybody talking back and forth. The good thing was that this contractor had a good amount of data on the 1L mix performance and had used it on a lot of other projects that wasn't mass concrete. So he had a great history. So this was an easy one from that perspective. So after some back and forth, structural engineer record came back and he said, all right, here's what the tolerances are, here's where I want temperature limitations to be, and we did some additional testing. So the contractor supplied data, had this, so we've got some good data here. It was decided that the max temperature is going to be 160 and the maximum differential is going to be 50, which was actually very lenient. Usually it's 35. This was very lenient at 50. And that looked pretty good. Again, this is going to be a June placement, central U.S., and scheduled for late June, and it was going to be completed over a 2-week period. The biggest challenge we encountered during this entire discussion was that after the grace period there of, hey, we can use a 50 differential, the concrete producer said, great, I'm going to deliver concrete at 80 degrees. That's not something I do very often, obviously, other than wintertime, but that's what they wanted to do. They wanted to be able to deliver a hotter concrete because they didn't want to use ice or any cooling mechanisms. They said, well, we don't want to guarantee it, we don't want to spend the money, we want to be able to do this, and according to this we can. So the challenge was then to, again, that educational piece about what you're going to have to do for your thermal control plan to make that happen. And because the slab was a bigger concern in a huge area, and again, this is a nitrogen plant, it's going to get covered in fertilizer, so you can't run cooling pipes through it. You can't do a lot of the other things you would do in a smaller footing or a wall or another shear wall kind of situation. And so I started to do the modeling, and it just flat out didn't work. Again, I had the experience now from doing the state bridges with the 1L, looking at their data, looking at their maturity curves, and saying, wait a minute. If this concrete's over 70, we're going to have a problem. And of course, they're screaming and yelling, oh, we can't get it down that low in the middle of summer. So it went back and forth in the whole thing. The good thing is that in the end, it actually worked. I had data that said, you're right. I mean, I gave them as much as I could possibly squeeze out of it. And I said, look, this is the absolute most it can be. And if you do this and anything goes wrong, all bets are off. You really have to have this control in place. They rolled the dice, and they got lucky. The 1L actually performed extremely well. This was a very easy thing for them to do. They had really no significant issues at all. It underperformed in the heat generation. It was cooler than I thought it would be, which was amazing, but it really was. The differential was right in line, and the strengths were phenomenal. So on this particular one, the lesson learns were, first of all, because there was a big mix-up in the first place, review your plans and specs first, and make sure you don't have parameters that you're not agreeing to. The best part about this was the producer had a ton of 1L history, had a lot of data to support what they thought was right. They had experience working with it. They were trying to tell me, you know, don't worry about it, don't worry about it. Of course, my job is to worry about it. The engineer was great to work with. Once they realized that this was in there, it was an oversight, we were able to get that fixed. Compliance equals performance. The reason I threw that in there is because with mass concrete, you have a lot of focus on the details. Everybody's worried about the thermal profile, the adiabatic temperatures, the differentials, the loss temperature, all that stuff. Compared to a normal or a regular concrete placement where they just place it and kind of forget about it, mistreat it, strip the forms really quick, and let it dry out. With mass concrete, more eyes, more paying attention, more following the rules, more communication, more pre-construction meetings, real history review, people looking at the details in the data, that absolutely paid off. So when you follow the ACI guidelines, you know, that are already in there, my experiences was, hey, this worked out pretty well. This next one here is the last one I have here, and this is a high-rise office building, again, central U.S. This one is kind of interesting only because they use the word massive concrete. That's really impressive. Massive concrete, you know. And again, I didn't make that up. That's what it says. But look at what I bolded here for your temperature things, and I think you already know why I'm freaking out. So the last guy scared me to death because he wanted to do concrete at 80 in the middle of the summer on mass concrete at 5.5 feet. This is 5 feet deep. This is 100.5 feet long and 71 feet wide and 5 feet deep. And this spec says they can do it to 95 degrees. And I'm like, wait a minute. You know, I'm getting better at this with the 1L, but I'm not that cocky. And max temperature 160, a 50 differential, all that other stuff. And the little clause that says, and after you're done, you can't let the temperature drop by more than 20 degrees in 24 hours. And that's a tighter control. That's a nice tight control in there. Somebody's really going to be paying attention to keep that in check. So this is, this had a lot of information on it, but so placement up to 95 degrees of mass concrete scared me. Max temperature of 160, differential of 50, max cooling no more than 20 in 24 hours. And that the only really, really good thing on this was talking to the structural engineer on the very first call, he was dialed in. That guy knew exactly what he was doing, had exactly specified what he wanted, and really was a great conversationalist about the data. So I could have nice data conversations with him, talking the same language. Bad news, obviously, is the contractor sees what they want to see in the spec, even though the engineer had another plan in his head. So a little bit more tricky that way. Make sure this goes the right way. There we go. Okay. So the original mix for this project, this one was going to be the 1S38. This was not going to be the 1L. This is the 1S38 that they ran out of material and said, by the way, we're only going to give you 1L from now on. So this is the one I started with in the first place. So they had done all kinds of stuff on 1S38. I mean, they spent good money using a lot of firms, doing a lot of testing that my company doesn't do. You know, some of the big names out there. And they had done calorimetry testing and maturity testing, and that was great until the 1L hit them. They didn't have 30 sets of data on 1L. They didn't even have 15 sets of data on 1L. And so this one took a little bit of a detour. So this is the one that I started in the beginning that you can imagine how many phone calls happened with, what do you mean we have to do additional testing? This is the one where we had to pump the brakes. And this actually slowed down the schedule. There's just no two ways about it. General contractor was completely on top of the issue. Once that happened, held frequent meetings. The producers and the installers were all up in arms, but the general contractor was great. The structural engineer was great. And we had a lot of meetings to talk about what could happen, what might happen. But we were conservative on this one. So because this was so different, and because it was a big foundation, a lot of different parts and pieces, they said, well, let's do some additional testing. So we made some test cubes. There was going to be some 5,000-pound air-entrained concrete and 6,000-pound non-air-entrained concrete. So we made two giant cubes, one with air, one without. And so we formed these up, used the real mix, put it out in the conditions that it was going to be used in. Again, we were hoping to get this thing poured in June. We were making the test cubes in June. So we needed the real data. And so to make the assurances and the engineer get happy and all that other stuff, we did this mock-up, and I think it was a really good way to go if you don't have the experience using the material. So we did maturity calibration curves, got everything dialed in for the air and the non-air mix. You can see the performance there doesn't look very different. It looks pretty good. It's what you'd expect it to be. Here's the actual results from the air-entrained cube. You can see our center, our centroid mass, our mid-height exterior, and our top-side exterior. From that cube, you can see the minimum temps, the max temps, the indexing. And the 14-day average strength is phenomenal. And here's the non-air-entrained cube. Again, nothing out of the ordinary. Everything worked exactly the way we hoped it would work. Things look really good. And here's the lab tests to correlate with that data. So again, you're looking at placements that ended up happening in August by the time we got around to doing this. And there you go. So great looking data because we used the actual model. We did everything the way it was going to get done in reality. We used the thermal control plan the way it was going to get done, the amount of sensors, the amount of telemetry, all that other stuff was factored into that when we did that. Additionally, we have more data that plotted. So this is where in the actual building itself, this is where we put the sensors, and this is some of the data that came from that. So we monitored and reported the thermal data through the midday of September 19th, 2023. Hit a max temperature of 141, measured on September 8th. And you can see the temperature plots there, that the removal of the blankets began on September 11th. In figure 2, it's showing you that the probe temperatures and the maximum temperatures for differential at 8 a.m., just prior to them taking the forms and the blankets off, everything was great. Right, this is the one where they stripped a little early because I got cocky. At 8:15 on the 12th, the temperatures of the near surface stuff cooled to about 32 degrees on the north side and 29 on the other. That was the max 20 because they ripped everything off too quickly. Those exceeded the project specifications, and we let them know right away. We let them know that it happened. So they turned around and they resumed it and they reblanketed it, covered it back up, put additional materials on there, and the rest of the project actually went pretty slick. So when you look at the data that we did in a subsequent placement, everything stays in check. So here we have the surface of the mass concrete. It warmed during the day to about 108 degrees, cooled to about 99. The max temperature differential was about 42, which again, 50 was their limit on this project. And there was no additional decrease beyond 20 degrees in a 24-hour period for the remainder of the time and for all the subsequent pours that we did on this particular foundation plan. So after the data was reported indicating that everything was fine, they continued on behaving themselves and not trying to rush the program anymore. Again, they were trying to cut corners and get it out slicker. So this was the actual lab test data for those placements that I just had up there. There's the no air mix and then the air and trained mix. And you can see what I have down there for the break data, and it's through the roof. So from our perspective in using the mixes, the 1L cement is performing extremely well. Again, not in the 10 or 12 hour range, but in 7, 28, 56, phenomenal. I'm not so worried about finishing or any of those other characteristics in mass concrete because of what that is. So the lessons we learned on this particular one was this. The relationships equal success. The contractor, the structural engineer, the consultant, all were able to talk to each other. Everybody was friendly. The fact that they were honest about what went on, that we didn't have the right information, that we had to try a new mix, that we wanted to do a test panel, it delayed the overall set. We wanted to place this in June. It got placed in the beginning of, or in the middle of August, so it delayed it 2 months. The owner was notified. Everyone was notified, told them this was the best way to go. It actually worked out all right. In this case, again, with mass concrete, quality and safety over schedule was the right answer. Compliance and performance, and obviously the ACI guidelines are the thing that really kept us safe. So the final lessons learned from all of these things together, you're probably sitting there going, wait a minute, I thought I came to a 1L presentation. He's been yapping around mass concrete this whole time and only said this much about the 1L. And you're right. You're right. Our experience on these 3 projects represents data over a 1-year period, different applications, including piers, walls, interior pit slabs, generator slabs, exterior slabs, bridge supports, footing, double stack slabs. It included 1L cement, 1L cement with fly ash, 1L cement with slag, 1L cement with slag and fly ash, if you saw those different slides I had up there. And we've got over 100 different sets of concrete cylinders from these projects with the data to back up that, along with maturity curves and everything else that we did as well. And so my takeaway was that when you follow the rules and you follow the ACI guidelines and you do good communication, in this type of application, your impact is negligible. It's really not much of a big deal at all if you stick by the rules and you do all the things you're supposed to be doing. So this isn't my testimonial of, yes, use 1L cement for everything universally. It's just a commentary about how pre-task planning, data-driven decision-making, team communication, and sticking to the industry standards really is what benefited these projects. Again, obviously there's a reduction in CO2. It's a greener product for our environment. But there was really, from a constructability standpoint, there was really no difference in how that was done compared to a regular 1-2 mix. So, I'm thinking that my takeaway was probably because of the better oversight, better planning, and better attention to detail, and then maybe limiting the speed at which we try and get all this stuff done. That's what yields the better outcome in the long run. But maybe that's the solution to half the problems anyway. Talking to each other, looking at the data instead of opinions, and then keeping an open dialogue and being respectful. Maybe that's just the way to build better buildings in the first place. But anyways, we'll see how realistic this is as things continue to change, and thanks very much for your time.